Okay, so let's start now. So today I would like to tell about some new subject, which can be called dualities and combinatorial identities, or maybe something like materialization of combinatorial identity. Let me explain what I mean. Let's consider let's start with the Cauchy identity. Cauchy identity. I recall it. We are working in the algebra of symmetric functions. I call my notation, this is the set of Young diagrams. And this is the basis of short symmetric functions. The Cauchy identity is probably the most important identity, a basic identity in the theory of symmetric functions, and it looks as follows. So we assume we have two sets of variables, x and y. And the identity, I recall it, is as follows. The sum over all Young diagrams, the Schur function in these variables times the Schur function in the second collection of variables, and the equality is as follows. The double product of indices So I recall how to understand this. In principle, there are two ways to look at this. One can say that both sides are elements of the algebra of formal powers series. And another possibility is to restrict to specialize the variables to some finite collection of variables. So we can assume, so one can restriction to finitely many variables. So we can assume, what is this? Okay, is it okay? There is something here, does not work. Okay, I hope So restrict to finitely many variables. So assume that we have only xm and for I greater than m, and likewise and the identity takes the form I will explain what this means. Something happens, I don't understand what happens. Никита, как вы думаете, тут у меня появляется сообщение, что трансляция экрана остановилась из-за того, что вы прекратили.
Мы видим экран.
Да, но я боюсь, что если я нажму приложение, опять что-то, что тут происходит, какой-то сбой. Непонятно для меня. Не знаю, что это означает. So please look at this and this identity. And the idea is to give it some representation theoretic meaning. Namely, we want to interpret the both sides of this identity as some characters of some representation. Representation of what? The idea is to construct a representation of a group. Take the group G Lm times GLN. So I mean the GL complex general group. Let's call it, say, G. And the representation space is the set of polynomials. This is my notation with, this is my notation for the polynomial space on the set of matrices of size M cross N. So we take the space of matrices of rectangular matrices with M rows and N columns, and the action and a representation of this group, the representation of this group is constructed as follows. Representation T, say TMN, representation GLM cross GLN. Given an element of this product, say G1, G2, which is an element of this group, and we assign to this couple of elements an operator which acts on a function, a polynomial function, and the result at a point x, and here x is a matrix here, is as follows. So we multiply by G2 a G1 transpose. So look at this formula. If you want to have a representation, we need to use the right action on the argument. This is a general rule. If you want a representation, we need to, using a change of variables, we need to change the variables according to the right action. Then we get a left action on the functions. Okay, so I recall it. So the idea, the claim is now as follows. Claim. So this representation T, claim T, N, is equivalent to the direct sum of irreducible representations with multiplicity 1. So the sum is over all Young diagrams such that the length, I forgot to mention it, the length is less or equal to minimum from M and N. And here we have some representation, some irreducible representation of one group, tensor product with representation of the other group. And this is the claim. This is the claim. And I want to say that this representation theoretic formula is essentially equivalent to this combinatorial identity, because the left-hand side of this formula is just the character of this representation. Indeed, we have a product of two short polynomials, and this product gives us the character of this representation. And the direct sum leads to the sum of characters here. Okay, we can say that the sum is infinite. Okay, what means the character of this infinite dimensional representation? It's not important, because if you wish, one can introduce some extra parameters, say t, extra parameter, which defines as a grading. Because we can view this representation, our representation, as a graded representation. It's infinite dimensional, but it is realized in the space of polynomials. And the space of polynomials has a natural grading by degree. And homogeneous components of this grading are invariant subspaces. So we can still speak about a character. Namely, we can introduce, if you wish, we can introduce here some additional parameters. Say t raised to the power, which is equal to the number of boxes of Young diagrams. And here also we can introduce this extra parameter so that it will become responsible for the homogeneous components. So we can view this formula as it's infinite, but it makes sense, in the sense that if you want to specify some concrete degree, say to specify a concrete degree, say D, we just need to keep the terms here with which count for Young diagrams with the number of boxes equals to D. Is it clear what I want to say? This is just a way to avoid infinite dimensionality of representations. Are there any questions, maybe?
It's not entirely clear where should T be on the right of this formula.
Sorry, I don't understand. Misha, repeat, please.
Where does the T should be on the right of the formula? We have T
on the right. Yes. You are right. On the right, it's here. Okay.
Okay, I see. So actually, this formula that, like, we have formal power series with coefficients somewhere, like in the.
Yes, we can. We have here. We have something like this. No, we don't need power series. No, okay, if you introduce this, we have, okay, so we can. Okay, something like this. Or maybe one can introduce T inside if you want. It does not matter. It doesn't matter. Okay, so it makes sense. So I repeat, the claim is that this identity expresses the fact that this is a character of some representation which is reducible, and this is another way to compute the same character. Why? Let me explain this. At least a formal argument. Is as follows. So we have the ring of polynomials on the set of matrices. Okay. And this matrices is built from boxes which are enumerated by indices I and J. Okay. And this can be written as the product, as the tensor product of the boxes. Of the ring of polynomials in one variable. So I would like even simply to write it as follows. Okay. To compute the character, we need to restrict to the subgroup of diagonal matrices. This diagonal matrices is in one GLM and another And if we look at the action of these two commutative groups on this space, and we see that the action for fixed I and j, okay, the action here is just as follows. A function of one variable, say, maybe I need some polynomial in one variable. And the action takes the form f is transformed. Let me write this a bit informally. Okay, and we want to compute the character of this action, and to do this rigorously, a bit rigorously. We want to do this taking into account this extra parameter in order to restrict to some concrete degree of t. Okay. So in degree t, in fixed degree d, we have the action on monomials of degree d. So the character is d. So we want to take the sum over d. And to do this more rigorously, we multiply by this. And this gives us this expression. Okay? And then we take the product over all I and j, and this leads us to this expression. And the product here, why we need to take the product? It corresponds to the fact that our representation on the whole space of matrices can be represented as a tensor product of characters on the spaces of polynomials in one variables. Is it clear, or maybe something is not clear? Any questions, maybe? So I tried to explain how to interpret the right-hand side, this expression, as a character in another way. So we computed the character of the same representations in two ways. One is obtained by using the decomposition into irreducible components, and the other way is just to ignore any decomposition and just look at the action on the space. Is it clear? May I continue?
Everything's clear, I think.
Is it, Misha, do you have some questions?
It is clear, I think.
It's clear. Okay, so don't hesitate to ask me if something is not obvious. Okay. So what I want to explain next. So here we have an example. So maybe some remark. because in this decomposition we have a multiplicity free sum, because as representations of the product, you have here a representation of a product of two groups. As a representation of this product, we have a multiplicity free sum. And this just means, at least informally, but it can be formalized, that the action of each of our two groups generates the commutant of action for the other group. So the situation here is like the Schur-Weyl duality. But let me explain some dual version of this. What is dual version? It is related to the so-called dual Cauchy identity. Dual Cauchy identity. First, the combinatorial form. It is written as follows. We have again the sum of all Young diagrams. But here we transpose the diagram. This is my transpose. Young diagram. And the result is as follows. How to prove this? One idea is to use, I recall that, so let me just give some sketch of the proof of this identity, how to reduce it to the Cauchy identity. The idea is as follows. The Cauchy identity, there is some close link, Cauchy identity, and Jacobi-Trudi formula. Jacobi-Trudi formula. I recall what is the Jacobi-Trudi formula. It looks as follows. With the assumption that I recall that the H's are the complete homogeneous functions, which are a particular case. This is a particular case of a Schur function, which corresponds to one row Young diagram of length n. And if we know the Cauchy identity, we can derive from it the Jacobi-Trudi formula, and actually vice versa also. But now one can read, for instance, in MacDonald, or maybe there is a nice book by Sagan, the dual Jacobi-Trudi formula, which is as follows. Dual Jacobi-Trudi. Which says the following. I'm sorry, I forgot to say what is here. How to understand this. Because we have here a determinant of a matrix. But because of this, I recall, because of this convention, this matrix is almost unitriangular, which means that it has the form like this. Here we have 1, 1, 1, zeros, and so its determinant is well defined. We can truncate this infinite dimensional matrix by some large number, and the determinant does not depend on the size of a truncation. It's enough to take. It's enough to take to restrict the I at j by the number of non-zero, by the length of lambda, which is equal to the number of non-zero rows. Okay. If you take some greater number, the result will be the same because of this special form of a matrix, which in turn, I repeat, follows from this. Okay. Now I return to the dual Jacobi-Cauchy. It looks as follows. And here we have elementary symmetric functions, which correspond to one column Young diagrams. And the difference here is that here we have to transpose our diagram. But if we know this, we can introduce the involution in the algebra of symmetric functions, which is defined as follows. The H functions are switched with the elementary symmetric functions. It is denoted by omega, the notation of MacDonald. And then it turns out that finally, to reduce dual Cauchy to ordinary Cauchy, identity suffices to apply omega to the collection of variables. So look, this. We can view this as something lying in the ring of functions which are partly symmetric in x's and y's, and applying omega to this group of variables, we turn this identity, this, one can say that applied So this is the idea of a proof. But now this is not a complete proof, but some idea of a proof. But now what I would like to say, I would like to give some representation, theoretic sense, some meaning to this identity. And how to do this? Again, restrict the number of variables. Of dual Cauchy. So assume again that we have finitely many variables, the axis, finitely many variables y, and the restriction of lambda is different. In the Cauchy identity, in the Cauchy identity, we need to have so in the case of finitely many x's and finitely many y's, we need to impose some restriction to lambda. And this restriction to lambda is like this, just it. Which means that this is because by the very definition, infinitely many variables have this equality if so this is the origin of this restriction. Okay. But in the dual Cauchy identity, the situation changes, and now we have something different. We have another system of restrictions. We have and what this means? And this means that lambda, the diagram lambda, is contained, must be contained in this rectangular shape. So it must be something like this. So we have only finitely many possibilities for our lambda, and this sum is now finite. It's now in the case of finitely many variables, of course. In infinitely many variables, it's infinite, but in finitely many variables, it is finite. So actually, we have the following. I would like, maybe it's better to rewrite it. we have this one. Boundary is contained in this shape. So it looks something like this. This is our lambda. And here we have a polynomial. This is a polynomial, not a power series. We don't need even to introduce some extra variable t. So this is a finitely dimensional, completely finitely dimensional situation. But how to demonstrate some strict similarity with the ordinary Cauchy identity? The situation changes here as follows. The change is related to replacing polynomials, which is more or less the same as the symmetric algebra on the dual space, by exterior algebra. Exterior. So the idea is that this identity both sides of these identities are characters of a representation of the same group but on the exterior algebra. Instead of symmetric algebra. And the characters are computed in two different ways. So one way is to compute the character by decomposing the representations into irreducibles. And the other way is just to look at the definition of the representation and compute its character directly. Maybe it's better to explain now, but what is this space? Maybe I would like to say all this in a little different way. So the space in polynomials. We have polynomials in variables So Z is, capital Z is my matrix. Write it as follows. Where A ranges over M and I ranges over N. And Lie algebra generators. So I will use the notation. The matrix units. And these are the matrix units. So this is the Lie algebra of GLM. And this is the Lie algebra of GLN. And the action is as follows. The action on the polynomial space is given by the following formulas. Where one can verify that this is just the action of the generators of this algebra. And for the generators of this algebra, the formula are very similar. They are as follows. So to pass from one algebra to another algebra is it's enough just to transpose, interchange with indices A and I. So the formula are symmetric. Here the summation is over the first index, and here the summation is over the second index. And all this happens, and this happens on the space of polynomials, polynomials in the variables Okay. But now there is an analog of algebra of polynomials. This is the Grassman algebra. What are the polynomials? Polynomials are defined by the assumption that they commute. So this is the free commutative algebra. But now take the Grassman algebra. Or the exterior algebra. The same variables, but we assume that they anti-commute. So instead of, so we have polynomials, case, or symmetric algebra. We impose the anti-commutation property, and we get the Grassman, or the exterior algebra, which is finite dimensional. But we can introduce just the same formulas as above, just the same formula as above. So we can define this, the action we define. We can define the action of the Lie algebra. Which corresponds to the Lie algebra of the product of our group. We can define this representation on the Grassman algebra just by the same formulas, but we only need to explain what means this in the case of Grassman variables. But there is no problem. This is the Grassman, so maybe it's better to use some other notation. So assume that we have to simplify things, but we assume some k Grassman variables. And we have the algebra. And with Grassman variables, it is spent by monomials we can assume that the dimension is equal to has finite dimension equal to 2 raised to power k. And what means multiplication? By some variable. Okay, this is just, we have some monomial. And right in front this one. If this monomials contains this letter, the result will be equal to 0, because if you have here somewhere the same letter, we can put it in front, which results maybe in some sign plus minus 1, which it depends on the position of these variables here. And we use the effect that in the Grassman setting, all squares are equal to 0. Okay? And what means the differentiation? Likewise, we look at our monomial. And there are two possibilities. If there is no right here, then the application of this differentiation is equal to 0. If the I is present here, we can put it in front, which results in appearance of some possible plus minus sign. And then application of this just means that we remove it. Okay. And it turns out that the necessary commutation relations between the generators of our Lie algebras are satisfied. And in this way, we get a representation, a Lie algebra representation on the Grassman algebra. And again, we have the duality in the sense that the action of one group commutes with the action of the other groups. And moreover, the commutant is generated by the action of the companion algebra. And this is reflected in the fact that the decomposition is multiplicity free. Another claim that I would like to formulate is as follows. We know that any irreducible finite dimensional representation is characterized by its highest weight. And here we have representation of the product of two groups, so no problem. Any such irreducible finite dimensional representation also possesses some highest weight vector, which is unique up to a scalar product. And so a natural problem is to produce, to explicitly write down the highest weight vectors in our realization. So the next topic is explicit form of highest weight vectors. Maybe I will use the terminology of boson case, or the symmetric algebra, or polynomials, and the fermion case, which means Grassman algebra. So in the boson case, so what we want, we are dealing with polynomials, and we want to produce some polynomial which is highest weight vector, both for the action of one GL and another GL. And what means highest weight? Highest weight, or sometimes it's called singular vector, means annihilated by the, say, n plus subalgebra. The key structural fact in Lie algebra, in our Lie algebra, is that our GLM or GLN algebra can be decomposed as n minus the diagonal matrices, n plus upper triangular matrices. And so the highest weight vector is the one which is annihilated by n plus. This is the question of convention. One could take n minus, but here I want to take n plus, okay? Now the claim is as follows. So we need to find a polynomial in the boson case. Polynomial. So Z is my rectangular matrix. So Z, I recall it is, one can view it as a collection of variables. Okay, so this is a polynomial such that the conditions are as follows. So the action of raising operators, raising means that, so these are the matrix units. These are the matrix units which lie in these upper triangular matrices. So they have to kill this vector, okay? Another condition is similar, but for it is also killed by the raising generator. So these are, I recall, belong to one Lie algebra. These generator come from another Lie algebra. Okay. And we want also some condition expressing the fact that this polynomial is an eigenfunction for the diagonal matrices. Okay. So this means also that, sorry. Okay. And how to produce such a polynomial? Okay. So here I assume that for k which is greater than, so the problem is to find by the general theorem which expresses our duality, such a polynomial exists and it is unique up to a scalar factor. So it's enough to guess, just to guess this polynomial. And the idea is as follows. Introduce the notation. So we have our matrix, which is in general rectangular, M and N. And for any k, which is less or equal to the minimum of this number, let's denote by this symbol the k truncation. truncation of this matrix. So we just take the corner, the square corner of size k by k. So this is my truncated matrix. So by the very definition, it makes sense only for k satisfying this restriction, of course. And now the result is as follows. The result is as follows. We have to take, first we take the first truncation, which is simply a number, and raise it to the power this one, and multiply it by the next truncation of order 2. But this is a 2 by 2 matrix. So we take the determinant of this matrix, and we guess already that what we need to have, raise it to this power, and so on up to maximal possible value. So we take z truncated of the order minimum of these two numbers. Say, I need some notation, so sorry. Let's denote it by L. And here we have lambda L minus what? Minus 0. So it's enough just to write this. So this is the result. And we claim that this is the highest weight. Highest weight vector. And this is easy to see just from the form of the action of this matrix units. I recall I wrote the action. It's here. Okay. What means this? Which means that we remove one variable with index b and I and replace it by this. Okay. And using the fact that a is less than b, one can see that after application of such operators, we get the required formulas. Okay. But what happens now in the Grassman case? So in the Grassman case, what happens here? In the fermion case? In the fermion case, what happens? So I recalled how to guess. We have again our matrix Z, but I propose you to guess what is the result. The diagram, the condition on the diagram is as follows. We have some shape. Which is contained here, something like this. Okay. How to produce a Grassman polynomial, a Grassman monomial, satisfying similar conditions. So we have to assign to any such Young diagram how to assign problem. Assign to lambda a Grassman polynomial in a natural way. The idea to use determinant is bad because we have anti-commuting variables, and what is determinant in this case is unclear. But could you guess what to do? And some hint is that the picture should be, in a sense, symmetric, because the rows and columns play equivalent role, parallel role. So the picture must be symmetric. Here, the picture is well symmetric because the roles of the x's and y's is evidently symmetric. This is because the determinant is invariant under transposition, under matrix transposition. So could you guess what to do here? Okay, one more hint. So assume to simplify, let's simplify. A general mathematical advice is try to simplify. If you want to get something, try to simplify. What means simplify? Take m, say m equal to 1. Okay, so now in this case we have only this one. Okay, so here we only have the variables z1, zn, okay, and you have representations in the exterior powers of our space. So we have a space Cn, okay, and you have exterior powers of this space, which are irreducible GLN modules. And what are the highest weight vectors of these modules? Any idea? No, we don't know.
We may
It's
take just the wedge product of these vectors of Cn.
But of course, we need to take these monomials are killed by these operators with I less than j. It's easy to verify. Okay. But okay, so this is the answer. But now, what we need to do in this a bit more complicated situation? So look what you do in this case. So we just place here Z1, Z2, Zk. And what to do in this case?
We should take some product over all boxes.
Yes, exactly. We just take something like this. So just take some picture. So we have some shape, say this one, for instance, this one. Just put here so take the wedge product of these variables in any order, because the order is not relevant here because of the antisymmetrization property. All possible variants differ by plus minus 1. So this is the picture here. And again, it's easy to see that such a polynomial, such a monomial, say this one, is killed by the raising operators which act along the columns or along the rows. Okay. So this is the picture. Okay, so finally I would like to mention the Schur-Weil duality. Schur-Weil duality. What it says, what I recall, we take this space, its tensor product, the action of a symmetric group, and times the G.Ln. And as a representation of the direct product, it is multiplicity free. And how to write this in terms of a combinatorial identity? Then the result is as follows. So assume that we have down the row Young diagrams or partitions, and this is the character table of a symmetric group. Symmetric group. In our situation, it is Sn, and we assume that so what this means? So by the very definition, one knows that the irreducible characters of a symmetric group are indexed by Young diagrams with n boxes, and the conjugacy classes are also indexed by Young diagrams of the same size. I denote them as rho. So this is the value of the character with index lambda on any element from the conjugacy class indexed by rho. And then the formula is as follows. The power symmetric function, I recall its definition. So what this means? This is the identity, some identity, maybe it's better to write here. The sum is taken over Young diagrams given rho. The sum is taken over Young diagrams of the same size. And this is the Schur symmetric function. And the identity takes place in the algebra of symmetric functions. And how, why this is the same as the Schur-Weil duality. This is just a combinatorial analog of a Schur-Weil duality. This is because we compute the trace of this representation in two different ways. So in one way, which gives us this term, which correspond to the right-hand side, it's similar to the right-hand side of a Cauchy identity. It is obtained just from the very definition. We want to compute the trace of the operator, which corresponds to the action of one permutation from the symmetry group of conjugacy type given by rho, and by the diagonal matrix with entries x1, x2, and so on. So what I would like to write this more directly. So this is what means this. This is just where P this is the power sum. So we restrict the number of variables by capital N. We have finitely many variables. And these are the definition of power sum. And rho is a Young diagram, so this is something like this. And we take just the product corresponding to the row length of the diagram rho. So now we compute for the left-hand side. For the left-hand side, we compute the action of permutation and the diagonal matrix. And an easy computation gives us just these quantities. Of course, evaluated in n variables. So this is the analog of a right-hand side, a direct application of the definition, of the very definition of a representation. But the left-hand side comes from the decomposition into irreducible components. This is the character of one companion, and this is the character, the Schur polynomial of the other companion. Okay. So this is a combinatorial interpretation of the Schur-Weil duality, and this is the Frobenius, the famous Frobenius formula. So this is the Frobenius formula, which is a key to the representation theory of a symmetric group, Frobenius formula. Which contains in a bit hidden form the whole information about the characters of a symmetric group. And the Schur-Weil duality is the materialization of this combinatorial identity. And here we again have some duality between the symmetric group and the GLN. So I told you about three examples, three dualities and corresponding combinatorial formulas, but there are many, many other examples. And for instance, the Littlewood formula, which I mentioned in my first talk, also can be can be related to some representation. And in the next lecture, I will try to explain what is the representation on the theoretic side of the Littlewood formula, which it is related to some infinite dimensional representations of some Lie algebras. And it's again related to the formalism of boson and fermion creation and annihilation operators, because the operator of multiplication by variables are creation operators, because they raise the number of letters, and the differential operators, boson of fermions, are annihilation operators because they kill some variables. So this is the plan for the next lecture. Okay, maybe some questions.